Good morning. So today we are doing the questions on equimomental particles. So the very first question is on your board. It is a very simple question and it is of dimension 1. Okay. Whenever you want to do a question, first of all see what is given in the question and what you have to find. Now what is given here? A uniform rod is given and you have to show that this uniform rod, whose mass is capital M, is equimomental to 3 particles. What are those particles? Those particles are m by 6 placed at one end, m by 6 placed at another end, and 2m by 3 placed at the midpoint. Okay, so you have to show that this system of particles is equimomental to the rod. Now let us begin it. The procedure is very simple. You have to find the moment of inertia of the rod about a line passing through its center and perpendicular to it. You know what is that? It is ma square by 3. We have already done it. Okay. That means now we have to find the moment of inertia of these 3 given particles about the same line. Okay. So, you know the definition of moment of inertia. It is mass into perpendicular distance is square. So, one mass is placed at a m by 6. It is at a distance a if 2a is the length of the rod. So its moment of inertia will be m by 6 multiplied by a square. Another mass is placed at b, m by 6 into a square, its moment of inertia. So that will be added to this moment of inertia. And the third mass is placed at the CG. It is 2m by 3. So its moment of inertia will be 0 because its distance from the CG, its distance from O is 0. So the total moment of inertia comes out to be ma square divided by 3, and we already know this is the moment of inertia of a rod length 2a and mass capital M about an axis passing through its center and perpendicular to it, and both are equal. So this is how the equimomental particles are defined. The moment of inertia must be the same, mass must be the same, length must be the same. I hope this question is clear to all of you. Now this is a very simple question of one dimension. Now let us pass on to another question, that is your page number 2. Another question is to show that moments and products of inertia of a uniform triangular lamina about any lines are the same as moments and products of inertia of 3 mass particles, each of mass m by 3, placed at the middle points of the sides of the triangle. Okay, so this is our next page number 2. Now let us pass on to page number 3. Page number 3, we are going to solve it. Now, how to solve? You are familiar with the method. We consider a elementary strip because you know that the triangle is formed by number of elementary strips placed close to each other, one upon the other. Okay, and to find its moment of inertia, we try to find the moment of inertia of one such strip, and then we integrate the result as the number of strips vary. So the procedure is already known to you because in the previous lectures I have solved the moment of inertia of a triangular lamina. So first of all, divide the lamina into strips. One such strip, consider one such strip PQ, which is at a distance x from the vertex A. Okay. Now, the triangular lamina, let me see the figure. This is the triangular lamina, and we have to find its moment of inertia first of all about AK. So the first thing which I told you I do is to find the density of the triangular lamina. How to find density? Mass is given to us, capital M. So capital M will be equivalent to integral 0 to h and then area of the strip multiplied by density. Now what is the area of the strip? Its length into breadth. Length is PQ, breadth is delta x. So it will be PQ into delta x integrated within the limits x varies from 0 to h. Why h? Because the height of the triangle AD is given as h. Okay. Now, our target is first of all to find PQ. Now, you can observe that the triangle APQ is similar to ABC, isn't it? That means x divided by h is equal to PQ divided by BC. Now what is BC? BC is small a. So we found the length PQ. PQ is coming as AX divided by h. Okay. Once you know the length, you can calculate the mass. Mass is, in place of PQ, just substitute what you have found, XA divided by h. So when you integrate, you will find the rho, value of rho as 2m divided by ah. Okay, so this is the first result we found. Now the next is, we have to find the moment of inertia of this strip about AK. So that is mass into perpendicular distance square integrated within the limits 0 to h. So that comes out to be mh square by 2. A very simple integration, you can work out easily. Now, so the moment of inertia about AK is coming as mh square divided by 2. Now the next is to find the moment of inertia about another line. One x-axis is AK, y-axis is AD. Now we have to find the moment of inertia of this triangular lamina about AD. Now how to find? We are going to use the theorem of parallel axis. First of all, we will find the moment of inertia of this strip PQ about AD. So we are going to use a result we know the moment of inertia of a strip or of a rod whose length is 2a about an axis passing through its center and perpendicular to it, it is ma square by 3. So the moment of inertia of this strip about AD will come out as 0 to h and then rho ax divided by h into dx, this is for mass, and in a bracket ax divided by 2h. Why? Ax divided by 2h because length of the string is ax divided by h, and we need half of the length of the string square divided by 3. So it will be 1/3 of ax divided by 2h whole square, as you can see on the board, plus the perpendicular distance square. Now what is that square? That is mn square. Now how to calculate mn? By the similarity of the triangle AMN and ADE. Okay, so mn is found as x square by h square into de square. Now tell me one thing, this de, we can take it outside the integration. Why? Because it is independent of the rod chosen. Whatever rod you choose, this will be the same. So when you work out this integral, you will get rho ah divided by 4 in a bracket a square by 12 plus de square. Now this de can be calculated easily, as I have calculated here. It is de, and de is nothing but be minus bd. Now what is be? Be is small a by 2. You know, in a triangle we write the sides as small abc and the vertices as, or the angles as, capital ABC. So it can be calculated, it is calculated in terms of small abc and capital ABC because the triangle is known and sides are known and angles are known. Now come to the next slide, slide number 3. Now what is slide number 3? First of all, moment of inertia about AD is found. It is given as the equation number, it is given as the equation number 2. Now after that we will work out the product of inertia of this triangular lamina about AK and AD. Now product of inertia is summation of mxy, isn't it? Now what is x, what is y, that is known to you. Okay, so you can calculate the product of inertia of the triangular lamina about AK, AD as I did, and you can transform the distances in terms of a small abc and capital ABC, so you will get the result 3. Now half question is done. We found the moments and products of inertia of the triangular lamina about AK, AD and AK-AD, about x-axis, y-axis and about x and y-axis. Okay. Now what is next? Next we will try to find the moment of inertia and product of inertia of 3 mass particles, each placed at the midpoints of the lamina. That means m by 3 is placed at one midpoint, m by 3 is placed at another midpoint, and m by 3 is placed at E, and we have to find the moments and products of inertia of these three mass particles about the axis AK first, about the axis AD next, and then product of inertia about AK and AD. Okay, so let us work out. So moment of inertia of these three mass particles about AK, it is found as equation number 4. It is mh square by 2. Again, you can match. This is same as equation number 1. Okay. Now next, moment of inertia of these three mass particles about AD. You can see this is also the same. Now let us pass on to slide number 5, which is the last. So you can calculate equation 5 and finally equation 6, and you can see that the result 1 is same as 4, result 2 is same as 5, result 3 is same as 6. That means we have obtained the result. What is the result? Moment of inertia of a triangular lamina about x-axis is same as moment of inertia of three mass particles placed at the midpoints of the sides of the triangle about the same side AK, about the same side AD, and the product of inertia about these two sides AK and AD. So that's all for today. Now next time I will be taking few more questions. So that's all for today. Thank you very much.